So these are like resonating structure we visualize over here. Hello everyone. Today we are going to discuss regarding the various chemical properties of aryl halide. As you are aware that we have already covered up the various preparation of this aryl halide, and both preparation and properties of alkyl halide. If you want to go through that, the link is being provided below. You can go through that. So today we will be discussing a bit regarding how these aryl halide react with various reagents, what are the mechanisms they follow, are they following the substitution reaction, electrophilic reaction, are they following the trend that we have seen in the alkyl halide. So as you know that in alkyl halide we have studied regarding three type of reaction that was shown by alkyl halide: nucleophilic substitution, electrophilic substitution, and reaction with metal. We have seen these three major types when we were discussing regarding the alkyl halide. So today we are going to see or visualize over here that all these three type of reaction, are they feasible with the aryl halide or not. So step by step we are going to move. The first thing which we are going to see over here is the nucleophilic substitution reaction. Nucleophilic substitution reaction of aryl halide. So before going into the depth of this, firstly we need to see the what is the difference between these alkyl halide and aryl halide. So if you visualize over here, let's say CS3, CS2, Br and C6, H5, Br. This one is the alkyl halide and this one is our aryl halide. So if you see over here that this bond, this halide atom is bonded with an SP3 hybridized atom. And while in this it is being, if we draw a bigger picture like this, so this bromine is attached to a SP2 hybridized carbon. So if you get into detail of this, during the substitution reaction, the nucleophile come over there and attack at this center. So why this reaction is being initiated? Because there is a electronegativity difference between them, which means here we call it as partial negative charge and here a partial positive charge is generated. That's why this reaction is being initiated. But in the same case here also, if you say like this, so but what is the major difference over here is here the SP3 and here the SP2, which means here we are having 33%, 25% S character, and in this case we are having 33% S character. So over here if you see, and this S character is more electronegative. We know the P character is more electron donating while S character is more electronegative or electron accepting. So here the lone pair, this lone pair is more towards Br side, but in this case this S character, due to this electronegativity increment of this sp2 hybridized carbon, it is not that much polar. This bond is less polar. Due to this sp2 hybridized carbon, that's why this reaction is not that much feasible as in the case of SN1. So one reason is this one, that why we are not this acid-1 reaction, or you can just nucleophilic substitution reaction, it was more feasible in this than compared to this aryl halide due to this sp2 hybridized bond attached to this aryl halide. So over here you can see this character. This is the one reason. We will also see some other reasons. This is our Cl, and this Cl, what it do? It is having this electron pair. It can come over here, and a resonance is being seen over here. And negative charge is being generated at this side, and now this negative charge, it can resonate around this at ortho and para position, because the Cl positive, or you can say halogen, they are ortho para directive. This again over here, the movement of electron take place Cl positive. So these are like resonating structure we visualize over here, and after that it will come down, and we are going to get initial structure only like this. So this in this you can visualize that there is a double bond character. This carbon Cl bond, it exists a double bond character, which means it is much more stronger as compared to CS3, CS2, Br or Cl, whatever. Here you can generally we over here. Yes. So over here, because we above side we have taken Cl, so in the blue side also we are taking Cl. In this case, there is no resonance possibilities there. That's why it is a single bonded atom or attachment. But here we are having a double bond character, and we know double bond is more stable than a single bond. But it is having a double bond character. That's why this bond is not that much easy to break down as compared with alkyl halide. So this was the second reason. This is the second reason why this substitution nucleophilic reaction is not followed by these you can say aryl halide. So I have just shown you one reason which we have visualized over here is a SP2 hybridization, which means the more electronegative, the electron pair are more towards halogen in the case of alkyl halide, but not in the case of aryl halide. The another reason which we have seen over here is a double bond character. We have seen a double bond character. This double bond character we can visualize over here, that this double bond character is making a carbon Cl bond much more stronger as compared to this alkyl halide and aryl halide we are comparing. So aryl halide CCl bond is more stronger due to a partial double bond character. If you visualize over here, it is a single bond, purely single bond, and is a partial double bond character. That's why this bond is more stable, more energy is being required to break down. That's why it is not that much feasible to proceed through the substitution reaction. So another reason, if we see, if we are this is a electron rich moiety. 3 pi bond are electron rich. It is an electron rich group. Benzene is having 3 you can say pi bond are there, so p orbital are there, some electron cloud is there, electron rich or electron cloud. That's why it will repel the nucleophile to come nearby this benzene ring. This will repel the nucleophile to come toward this benzene ring. So this is also a reason. So the third reason I have shown you why this nucleophilic substitution reaction are not that much feasible in the case of alkyl halide as compared to the aryl halides. Now one more reason, that is specifically for SN1 reaction. Why it will not follow the SN1 reaction? In SN1 reaction, what happens? Formation of carbocation takes place. So if this bond is broken down, this plus C positive charge and Cl negative, then the nucleophile comes and attack over here. But if you see over here, this is a, you can say, aryl carbocation. It is a aryl carbocation, and we know these aryl carbocation and the vinyl carbocation that are less stable. So this SN1 reaction is not being favorable in the case of these aryl halide due to the formation of the intermediate, that is a aryl carbocation, that is very unstable, not that much stable. So that's why I have shown you why this nucleophilic substitution is not feasible, and one specific reason for SN1 reaction. But if we put down some drastic conditions, some pressure is being applied, some temperature is being raised, which means that condition that are not normal conditions. So in that condition, we can just get this to be done. So for that, what we need to do, we need to take chlorobenzene. This chlorobenzene, when reacted with NaOH in presence of temperature and pressure, nearly 628 Kelvin temperature and nearly 300 around atmospheric pressure. So these are the necessary conditions in which we provide the NaOH aqueous and 623 around or 628 Kelvin temperature and 300 atmospheric pressure. So this is the way how we this is aqueous. If we are using, so what is going to happen over here? We are going to get a O negative Na positive. Why? Because the base is present and that base can accept this O negative. So now this will, if we work up this in the presence of dilute HCl, so we are going to get a product like this, phenol. And this is also an industrial process. It is an industrial process or manufacturing of phenol that we are going to discuss in quite detail in the alcohol, phenol and ether chapter, and this is a Dawes process. And if you get into the mechanism of this reaction, how this reaction is following, how this special reaction is following, so you are having this this is our OH negative is there, we are having OH negative. So this will abstract this base. This is going to take this base from here, and so over here a negative charge will exert over here, and this negative charge, it will give rise to a formation of benzene. Benzene, a very unstable intermediate is being formed through this process, and this benzene can be reacted with OH from any of the two sides. Either it can attack from this side or it can attack from this side. So if we are attaching this OH negative over here and here a negative charge, and carbon negative is more unstable, so it will abstract this proton from here, O negative, and this hydrogen. and after that this dilute HCl, or by the workup, what we are going to get over here, this is the product which we are going to get over here. This phenol, this is the whole mechanism. Firstly, the abstraction of this proton and this benzene formation, attack of this OH negative, and we are going to get the phenol. So this is a drastic condition, it is not a normal condition. We have to give a higher temperature, nearly 623 Kelvin, and a higher temperature, that is nearly 300 atmospheric pressure. So higher atmospheric and temperature and pressure, we can react this alkyl halide, or you can say chlorobenzene, in presence of NaOH aqueous, we are going to get a phenol through a Dawes process. So this is a reaction that is showing us a substitution reaction. Generally these Aryl halide, they don't show the substitution reaction. They don't show the substitution reaction. But now we will see in the next upcoming video, we will see the reaction with metal of Aryl halide and electrophilic substitution reaction. Electrophilic substitution reaction of Aryl halide. So that's all for today. Thank you. Have a nice day.